How you doing, man?
I'm good, buddy. Good
Paul
to see you
Mercurio.
again. Good to see you again.
Professional comedian. You got your own podcast.
Yeah, Inside Out.
Out and In.
There you go.
In-N-Out Burgers.
Yes.
Did they sponsor you?
Yes. For those listening and watching, this is how not to host a show. Have a guest and not know anything about it. Yes, it's called In-N-Out Burger, and the whole podcast is me interviewing people in the drive-through window.
In the drive-through window.
You want fries with that? So, you're an astrophysicist. The guy was on my podcast.
I was.
Along with Paul McCartney, by the way.
Oh, no, okay. All right.
What do you mean, okay? That's all you say?
Name dropper.
Yes.
But none of that impresses me as much. You've got like a Peabody Award and an Emmy Award. This is for writing. You've been
writer on the Daily Show, and I worked on the Colbert Report.
We love you, man.
I love you too, man.
Thanks for spending some time with us here.
Absolutely. Always great.
Making this happen. You know what we're going to talk about? Mm-hmm. The cutting edge of cosmology. Because everybody's talking about cosmology all the time. But who gets in there and say, where's the edge?
Yeah.
And where are people at fisticuffs?
Yeah. we like to mix it up here. Where can we get people at each other's throats?
At each other's throats. Because then that's actually, the history of science shows that's how discoveries emerge.
No, I have to say, I've been doing a few of these with you, and this one is really cool, really interesting, because there is a lot of back and forth on this, and it's really compelling.
Yeah, no, it's good. And a lot of people, contenders, I think is the way to think about that.
Yeah.
So we combed the universe to find who would be ideal in this conversation. And we found an old friend and colleague of mine, Adam Riess. Adam, welcome to Star Talk.
Thank you for having me.
Welcome to my office here at the Hayden Planetarium.
Excellent.
Yeah.
I was just wandering around the museum and you guys pulled me in. So.
He was with a bunch of children. He was and his hand was being held by a teacher. Yeah. He might be brilliant and have a Nobel Prize, but apparently he gets lost in large spaces, everybody.
So you're at the Johns Hopkins University.
Yeah.
You're the Bloomberg Distinguished Professor there.
I am.
Bloomberg, he's a friend of my wife who worked for him. He has a background in physics and engineering and came through Johns Hopkins.
Yes, he did.
And donated a whole building called the Bloomberg Center for Physics and Astronomy. Yeah, so there's some good Bloomberg action down there in Baltimore.
And then he ruined everything when he created bike lanes in New York City. I'm telling you, let's spend an hour on that, Mr. Nobel Laureate. Can we fix that?
Says the man who does not ride a bicycle.
Exactly.
Okay. Many people don't know that the Space Telescope Science Institute which was responsible for receiving all the data from Hubble and other telescopes, spaceborne, is co-located on the campus of Johns Hopkins University.
That's right.
So you also have a position there as well.
That's right. That's where we have the joystick.
Okay.
I'm going to leave that right there.
We have to add that you are a Nobel laureate.
That's right.
That's badass.
Yeah.
And I think if you had a business card, just say Nobel. That's all. You don't need anything else.
No phone number.
No phone number.
You just think you want to talk to him. He's so smart, he calls you.
So remind me, what year you won that?
We won it in 2011.
You won the Nobel Prize, and that year was split three ways. So who were the other two recipients?
Brian Schmidt and Saul Perlmutter.
And Saul, I remember, was a West Coast guy.
Right.
He
led the Supernovae Cosmology project.
Okay. With the same intent of making the kind of measurements you were making.
That's right.
With Brian Schmidt.
Right.
Right. Okay.
Right. And we were members of the High Z Supernova team.
High Z would be high redshift.
Correct.
Supernova team. And it was given to you specifically for
the discovery of the accelerating expansion of the universe.
Which today we just call dark energy.
Well, dark energy is, we think, the driving mechanism for the acceleration. But there's still a lot we're trying to understand about the nature of dark energy.
Well, get back to work.
Please.
So, I'm going to say, welcome to Star Talk.
Thank you.
Yeah.
It's an honor to be here.
Yeah. And so, you are co-discoverer of because growing up, I don't mean growing up as a kid, coming through school, in graduate school, we always knew that there was this term in Einstein's equation that it referred to like a negative gravity or something. It was mathematically legitimate, but no one had a negative. What is that?
Nobody accounted for it.
No, what is it? It's just a math thing. So every time we had a conversation about the expanding universe, you had to explicitly say, we're going to assume this is zero. Because what are we going to do?
It's expanding at a constant rate, basically.
Or expanding only according to what the galaxies tell it to do.
Got it.
This would be an extra thing going on, okay?
And you were just too lazy to explore that?
No.
Is that what happened?
No, apparently this gentleman was not too lazy to explore it. And he's saying, I wonder if that is a thing. Okay? And there you go. Wait, so first, catch us up on being co-discoverer of the accelerating universe. There are these equations that I'm describing here, and you're getting data. What was your data?
Sure. So, so as you said, this term that Einstein had put in, which he actually put in for a good reason. At the time, he thought the universe was static, and so this term was needed to balance the attractive gravity.
Otherwise, the universe would just collapse on itself.
Correct. Then it would just collapse. And then, so astronomers at the time told him the universe was static because they thought the universe was the Milky Way galaxy. They thought that was already everything. And of course, it turns out there are galaxies out there. They're moving further apart. Hubble and others showed that. And
Hubble the man.
Yes.
Hubble was a man before he was a telescope.
That's right. It's more like the RoboCop version of Hubble.
But he would be mistaken for a telescope at a lot of parties.
That's right.
He had the shape of the body of a telescope.
The famous story is that once Hubble showed that Einstein that the universe was expanding, in which case it was unnecessary to have this kind of repulsive gravity to balance things, and it was kind of dropped to the side. But as we know in physics, once something is possible, it is always there unless you have evidence that it doesn't exist. So,
right. Very important bit of scientific wisdom there.
So let's jump to the 1990s, and astronomers are looking for...
that was the 1920s.
That was the 1920s, yes. So we're in the 1990s now, and astronomers think there's some matter in the universe, and the question is there enough matter to stop the expansion of the universe? Like, launching a rocket, does it have escape velocity from the gravity?
Is that matter something that would later be called dark energy? Is that sort of...
No, this is what we call dark matter, at the time. We knew there was a lot of matter. Most of it was dark. We knew this because there was extra gravity, the rate at which galaxies or stars orbited galaxies, the stars would have flung out if there wasn't this extra matter. So we knew all that. And then the question was, is there the critical amount, the amount that would halt the expansion, or would the universe expand forever? And so by the late 1990s, the best way to do this was to measure the expansion rate of the universe in the past and compare it to the expansion rate in the present and see if it was slowing down enough to stop.
And this is where the distance ladder comes in terms of measurement.
Yeah, how do you know how far away? I mean, nearby, it's hard enough just nearby. I guess you can use parallax on stars.
Right.
But these stars are sitting on our noses.
That's right.
And we have whole galaxies nearby and beyond.
Right.
So what method, you had to really refine a method to do this.
Yeah, so parallax is great. Having a tape measure and running it out somewhere is great, but these just don't work very far.
You can get those at Home Depot.
Yeah, I know, but not one that long.
With your Home Depot tape measure, you can get to things that are walking distance of you.
Right.
All right. But there are stars out there that, you can't do, radar beaming to them because they're light years away.
So you have to use parallax, a form of geometry that had its limitations because of the angles of the geometry.
You're just trying to make up for getting something wrong a minute ago.
I didn't.
It's pretty good.
But that's good. You did good there.
Yeah.
You did good.
Yeah.
So if you have your two eyes, and if you can put your thumb, and you just look at your thumb with one eye, and then you switch eyes, and then your thumb is like moving back and forth.
Hang on, I need a manicure. Jesus. Wait, what am I doing now?
Yeah. You look at with one eye and switch eyes, and your thumb will shift back and forth as you shift.
Right.
It turns out the amount that shifts and the distance between your two eyes uniquely determines how far away your thumb is.
Which is then used...
So try this. Put your thumb here and do the same thing. So now it separates even more.
Yes.
So that's an angle. You can measure the angle. We know how far your eyes are. You know exactly how far away your thumb is.
do this with my hands so I don't have to look at you. Well, that works. Either way.
I'm blotted both ways. So what are our eyes? How do we do this with astronomically? Well, you can take a picture of a star, and there's a background stars behind it, and then 6 months later, take another picture of that same star. Now, the width of your eyeballs is the diameter of Earth's orbit. Now, that's good.
So now you can measure.
Now you get that, and you see how much it varies. You know how the diameter of our orbit, bada bing, we get the distance to it. And we have sent telescopes into space to measure this exquisitely, far beyond what's even possible from Earth's surface.
Right. Hubble and then Webb.
Very reliable. No. It's a telescope called Gaia. Gaia.
Yeah.
So now we trust these because it's like geometry. We got this.
Right.
But now you have to go beyond that, and you don't get to use parallax.
Right. So then you have to use another method, okay? And there are methods that we use here on Earth, like a lighthouse. So if you're a ship captain, you want to make sure you're far from shore. You want to make sure a lighthouse, which you know is very luminous, looks very faint and assures you, wow, I have to be far away. And we can actually do that quantitatively by measuring how bright the lighthouse actually appears. So I like
that analogy. It's a good one.
In the past, there was a class of pulsating stars called Cepheid variables that have this wonderful property that they tell us whether they're a very luminous lighthouse or a not very luminous lighthouse, depending on how frequently they pulsate. And they're about 100,000 times the luminosity of the sun. And so the big advantage is if you want to measure far, you better have a very powerful lighthouse.
Right.
So they were good for a while, but we had to go out much further.
That's the second rung of the distance ladder, right?
Yeah, I think so. Yeah, we call it that.
We could say that.
It's the third one after the Home Depot tape measure.
Right.
Yes, that's right.
So you said something important there. 100,000 times brighter than the sun, which means the sun at those distances, we would just never even see it.
Right. That's right.
It's not useful.
Right. That's right.
Yeah.
So the name of the game at this point is to be able to measure truly cosmological distances very far out. We're really just in search of an ever more luminous standard candle, something that you can just see far away. If you can't see it, you can't measure the distance.
And for me, explain the standard candle, and that my understanding is that we don't really know what that luminosity is.
So a standard candle is any object whose luminosity is uniform. So when we see a standard candle and it's uniform, when it appears dim, that tells us it's far away.
Right. And we know that we know why they're uniform. That's been determined.
Correct. We know we start out with very good theoretical understanding, and then ultimately we have empirical understanding, which shows us that. So by the 1990s, these Cepheid variables are just not luminous enough. We really need things that are billions of times more luminous than the sun, because we now want to look so far back that the universe has changed, that the universe is younger, that it was expanding at a different rate. So this requires us to go back billions of light years.
So it's like when you're a kid, you shoot up one summer. Neil's like
in height.
Yes.
Or shoot up drugs. I don't know. It's you.
I don't know what you were doing.
I don't know what you. I don't know what kind of child.
I'm from the streets, everybody. I grew up on the streets. No, you shoot up in height. Like in one summer, you go from 4'9" to 5'9".
Okay.
But then as you get older, it progresses slowly. So that's sort of the idea here. In very rudimentary terms, when you're going back in the early stages of the universe, you're going
back to the younger.
Yes. Right. Where the expansion is faster.
No, we don't know that yet.
Right. Well, it could be.
It could be slower.
Right. So let's not jump the gun. So by the late 1990s, we had known about supernovae. Gosh, going back to the ancient Chinese, a star would suddenly appear where you had saw nothing, and we came to realize that these are exploding stars that are billions of times the luminosity of the sun.
In fact, the very word supernova, nova means new in Latin. And so a really bright new thing called supernova, and only we would later learn that the star dying at the end of its life.
Right.
Yeah.
My wife calls me a supernova.
Dying at the end of
I don't know how to feel about that. But anyway.
He's still in therapy. We'll let him.
I didn't mean to look in your eyes when I said that.
So what we came to really realize in the 1990s is there's two completely different ways nature produces this kind of supernova explosion, and that's very important. One way is you have a very massive star that loses its ability to produce energy at its core. And producing energy was the way it produced pressure that held back gravity. And so it's a very dangerous thing for a star like this to lose the ability to do that. It's basically lost its structure, and so it will implode, followed by an explosion. And those are very bright. They're great, but the problem is they come over a wide range. That could have been a very massive star, or a medium star, or that could have been a star that when it collapsed turned into a black hole, in which case we'll see almost nothing.
So they're not as reliable as a standard candle.
So it's not going to be a good standard candle.
Not a standard candle.
But it's not a good standard candle.
Yeah.
And then we realize hiding in this distribution of all kinds of different exploding things was a subclass that were all the same. And that is a completely different mechanism. It's called a type 1a supernova. And that occurs when you have the core of an old star like our sun will become, called a white dwarf, which is in a very special state. It's holding itself up against gravity because of quantum mechanics, really. And it can only be stable up to a certain mass, known as the Chandrasekhar limit, after the famous Indian astrophysicist Chandrasekhar, who in the 1930s showed that a star could only sustain itself up to about 1.4 times the mass of the sun. So now imagine this. You have a white dwarf star. It's sitting there. It's less massive than this Chandrasekhar limit. Maybe it's the mass of our sun.
And minding its own business at this point.
It's doing nothing. And it would be happy that way. It would just cool off and live its whole life that way, cooling, radiating. But what if it has a friend? And, with friends like these, who needs enemies? These are a star orbiting that star, and they get too close, we think, and mass starts to transfer over, we think, and the details of exactly how this occurs are debated. But somehow...
How the mass transfers is not clear.
Exactly. Whether it's like they actually merged or it was a gradual process.
Can I just say something between Einstein and you guys? You seem to leave a lot of stuff off to the side. And we're not sure, but we'll just go whatever.
Well, because he's after the consequence of what happened.
That's correct. That'll be clear in a minute, okay?
Yeah.
Okay. So anyway, somehow mass transfers over, and when it reaches that Chandrasekhar limit, it's like, boom, a thermonuclear explosion runs through the star, okay? And what's so great about this is they always blow up at just about that same mass, very close to that. So this is a standard candle. This is something you recognize it far away. And how do we recognize it? It has a certain spectrum. It has a certain chemical fingerprint.
And this was observable within the Milky Way because that was a distance that we could observe this, or we
could observe these beyond. We could observe these at some of the most distant galaxies.
Because of the telescopes.
Right. Now, they're incredibly rare. There's only one in a galaxy like ours per century, but there's no real limit of galaxies. So if we can take a wide enough image that contains hundreds of thousands of galaxies and then come back, a month later, what turned out to be, so unlikely to happen is like guaranteed to happen. It's like winning the lottery because you buy all the lottery tickets, right?
Chuck, last year we all went to your comedy show.
Yes.
Right here in Manhattan.
That's right.
And what was the title? What'd you call it?
It's called Chuck Nice, Just Smart Enough Because I Sit Next to You.
No, we love you because you have a science literacy and you don't let anything by.
Yeah, well, I took that and I put it in a comedy special, and you were there in the audience.
Do you have a clip you can show us?
Absolutely. And just like if I were on The Tonight Show, I have no idea what it is. But check it out. I am too lazy not to believe in God, okay? Because when you ponder the origins of the universe, that gets very, very deep. A singularity, just that by itself. Something that is infinitely hot and infinitely dense. How can it be infinitely dense? At some point, you can't pack shit in anymore. Like what? And at that point, I'm just like, God did it. December 30th, you'll be able to come to Star Talk and you'll be able to see the whole comedy special. So bring in the new year with some science, dumbass. Please head to the Star Talk watch page on YouTube and tap